Okay, we're ready to work at Part F. Part F is where we have equal moles, same molarity and volume of both the sodium hydroxide and the butanoic acid. So we are here. Now you do not need to look at that and know that you are there in order to work this problem. You will work this problem as you would any titration problem. So let's just go about doing this, maybe not even realizing we are at the equivalence point. I will once again write the reaction that is taking place. The weak acid is reacting with the strong base. It's a one-way reaction. The strong base forces it to completion, producing A- and water. As a one-way reaction, I don't do an ICE table, I do an ICF table, and I put moles into the table. Now, as with Part B and Part C, the number of moles of HA is 98 times 10 to the minus 3. That hasn't changed. To determine the number of moles of hydroxide, we will know that that's equal to the number of moles of sodium hydroxide, and to obtain that, it will be molarity of the sodium hydroxide times the volume. Well, the molarity is 0.249 moles per liter times the volume of 0.02000 liters, and that's going to give me the exact same number as well, 4.98 times 10 to the minus 3, and that would be the moles of sodium hydroxide or the moles of hydroxide. So I'm going to put this same number here. Oops, my time's in there. 10 to the minus 3, none of this, don't care about that. I consume the smallest. Well, they both have the same amount. So I will subtract 4.98 times 10 to the minus 3 on this side. I will add 4.98 times 10 to the minus 3 on this side. This will leave me with no weak acid, none of the hydroxide, and we'll have converted all of that weak acid over to a conjugate base of the weak acid, which in this case is CH3, CH2, CH2, COO-, that's the butanoic ion. Okay, so now what do? We do not have a buffer. There is no weak acid present at this point. It has all been converted over to the conjugate base. So when you are at the equivalence point, you have got to go ahead and consider the equilibrium of what remains. So in this case, what remains is a weak base. We need to write that weak base reaction. So a weak base, A-, is my representation. When it's in the presence of water, it will do what bases do. As a weak base, it will be in equilibrium. It will accept a proton and leave me with OH-. Now, over and over again, I see students struggle with writing this reaction, and they kind of try to come up with some kind of shortcut. I don't want you to come up with some kind of memory device other than knowing that this is a base. It is a base. And as a base, it is a proton acceptor. So have it accept a proton from the water and do the proton swap. Since it's in equilibrium, I know an ICE table is appropriate. Now in an ICE table, you have to plug in concentration. You must put in molarity. So I'll write a big M here as a reminder. This is moles. I can't take that number and just plug it in here. I have to take this number and divide by volume. Now I have to divide by the total volume to get that number, because it's the total volume in that solution that I'm trying to figure out the pH of that total solution. So I know that the volume at this point is 20 milliliters for the acid and 20 milliliters for the base. So that's 40 milliliters, or 0.0400 liters. So that's the total volume. So to get the concentration of A-, it's going to be the moles of A- divided by the volume of the solution. And that's going to give me a concentration of 0.1 2, 4. I'll carry an extra significant figure for now. That's the molarity. And that is what goes into this table. 0.1245. Do not care about water. It's not part of my equilibrium expression. Before this reaction has taken place, I put zeros here and I work this because that's what was present. See, HA, we used it all up. Now this equilibrium is going to reestablish a little bit of HA. So some of it is going to get used up and produce some HA and some hydroxide. So at the equilibrium point, I have 0.1245 minus X. I have X and I have X. Now this substance is a base. I know that A minus is a base, and if it's a base, we don't want to use the Ka value that they gave me up here in this problem. We want to get the Kb value, so we're going to determine Kb. Kb equals Kw, which is 1 times 10 to the minus 14, over Ka of 1.54 times 10 to the minus 5. This is going to give me a value for Kb equal to 6.49 times 10 to the minus 10. Now that's Kb. What do we do with Kb? We take Kb, and we know that Kb is equal to products over reactants raised to the power of their coefficients. So Kb of 6.49 times 10 to the minus 10 is products. That's x times x, or x squared, over the reactant, which is 0.1245 minus x. Now let's look at this value of Kb. It's very, very tiny, so we can assume that we don't have to worry about that x term, and then we can quickly and easily solve for x. We're going to take 6.49 times 10 to the minus 10 times 0.1245, and then we're going to take a square root of that value, and that's going to give me x equal to 8.99 times 10 to the minus 6. We'll check our assumption. It's appropriate that x was very, very small, that we could ignore it. So as such, we can use this number. Now this x, if we look up here what x represents, it's the OH minus concentration. So we'll make note of that, because what we want to determine here is the pH. So we can first get the pOH. I'll come over here to the left to do that. pOH is equal to the negative log of the number we came up with, 8.99 times 10 to the minus 6. This is going to give me a value of 5.046. Now, many students stop here and say that's the answer, but remember, this is pOH, and we want pH instead. pH would be 14 minus that number. And this will give me a value of 8.954. Now, just a little word about this pH. If you are doing a titration between a weak acid and a strong base, the pH at the equivalence point will always be in the basic region. And we see this 8.954 value. That makes a good value for it. It is in the base region.